Hello again. It's me, Mr. Boothman. Last time I was telling you all about 1.6, and that was combining functions. Now we are jumping right into 1.7, where we will learn about one-to-one functions and inverse functions. Those names might sound a little intimidating to you, but don't worry. I'm here, I will guide you through it. You are capable of this. Math might seem intimidating sometimes, but you're honors pre-calc students, and I have complete faith in you and what you can accomplish. Let's start with one-to-one functions. We'll start with our definition. A function within domain A is called a one-to-one function if each output corresponds to exactly one input. So this should seem kind of familiar. This is similar to our definition for a function. If you'll remember, our definition for a function was that each input must have exactly one output. So what does that mean? That meant that whatever we put into our function, the function would give us only one thing back. That definition meant that for different things I'm putting into my function, it could give me the same thing back. That was fine, I said, as long as I was still only getting one output for each input, one y for each x. For a function to be one-to-one, however, we are restricting it a little more. We are saying that for some x that I'm putting into my function, whatever my function is giving me back, my output for that x, has to be unique. It cannot be giving me the same output that it gives me for a different input. Each input must have a different output. So, what I just said was probably a lot to take in, and I guarantee that you probably didn't catch all of it. I know I wouldn't have if I were watching this video, and that is 100% completely okay. If you need to pause the video, go back just, how long is this? I've been talking for about 2 minutes. You need to go back like a minute and a half, re-listen to that. That's totally fine. Do so, write down your questions, but we are going to move on and talk about some examples so we can see exactly what this means. So for these 4 examples, we need to determine if the functions are one-to-one. We are going to do that using something called the horizontal line test. Now remember, when we were testing to see if something was a function, we used what was called the vertical line test. That meant if we drew a vertical line and at any point on the graph it passed through more than one point on the graph, then it failed the vertical line test and it was not a function. This is the same exact idea, except instead of drawing a vertical line, we are drawing a horizontal line. And if it fails this test, then it is not one-to-one. Why? Because if it passes through more than one point, that means that for 2 different x values, the graph gave us, the function gave us, the same y value. Those were not different outputs, so it fails our definition of a one-to-one function. So let's go through a couple of examples at least. For these, I would graph these using my graphing calculator, using Desmos, using another website like Wolfram Alpha, if you've heard of it. Desmos is probably easier though. Or we can use our knowledge of transformations to sketch very quick graphs of these. I'm going to do that for A and B. I know that this -1 here means that my vertex is, or not my vertex, but where I would be at 0, 0 is moved down 1, and then I know that my cubic function looks something like that. And now I'll use my horizontal line test. For each point on this graph, it looks like it passes my horizontal line test. So this function is one-to-one. It's that easy. For B, again, I'm looking at the transformations. I know that my vertex is moved down 4. And I know that it's a little skinnier than usual because of that too. And I can see right away that at almost every point on this graph, it fails my horizontal line test. I'm passing through 2 points each time. That means that for this x value and this x value, it's giving me this same y value. For 2 different inputs, it's giving me the same output. That's not okay. Well, it's okay. It's not like the function's in trouble. But that means that the function is not one-to-one. Hopefully you're still with me. If you want, and I guess that sounds a little nicer than it should be. Not if you want, but I would like you to try these on your own. And we can talk about them in class. We can go over them in class. Those can be our examples when we review this video in class. Again, you can use software, you can use your graphing calculator, or you can use your knowledge of transformations to sketch those graphs. That's about it for one-to-one functions. Fairly straightforward definition and fairly straightforward test for them, the horizontal line test. Next, we'll move on to something that is a little more complicated. And I don't say that to scare you, just to prepare you. You might have more questions for this, and that is completely okay. Please write them down, bring them to me or to Miss Parker. And that's something called an inverse function. So let f be a one-to-one function with domain A and range B. Here you already see that we're using our one-to-one functions, our definition of one-to-one functions. That's why we just talked about it. Then its inverse function, f inverse, this is how we denote that, has domain B and range A. So you'll note that the domain and range switched for our inverse function. And it is defined by the function that takes the outputs of f of x and gives us their original inputs. In other words, it reverses f of x. It's the inverse. We find it by switching x and y in f of x and solving for y again. That was probably a lot to take in too. That's okay. Pause this video. Take a breath. If we just look at our definition, then if we think about it, then we know why our function has to be one-to-one. We know why I just talked about one-to-one functions at the first part of this video. The function takes each output of f of x and gives us their original inputs. So let's take an example. Just something like f of x equals x squared. So I know that for my original function, if I had something like f of 2, then that's 2 squared, which is 4. But I also have f of negative 2, it's negative 2 squared, which is 4. That means that when I take my inverse function, f inverse of 4, again, I'm taking in my original output for f of x, it's going to give me its original input. So my original inputs for 4 were 2 and negative 2. So for this f inverse, my one input, 4, is giving me 2 completely different outputs. That fails our definition of a function. So in this particular case, for f of x equals x squared, there is no inverse. It just is not a function. So that is why we care so much about our f being one-to-one. One last thing to note about f inverse is that it is symmetric with respect to the line y equals x. And don't worry, we will go through examples of this. It's symmetric with respect to the line y equals x. So we've talked about, with transformations, we talked about reflections, we talked about things being symmetric with respect to, we talked about even and odd functions with things being respect to either the y-axis or things being symmetric with respect to the origin. Now for inverse functions, we are talking about things that are symmetric with respect to y equals x. And that is in comparison to its original function. So f of x, if we reflect that over the line y equals x, will give us the inverse function. So if I have the cubic function, and I have the line y equals x, then my inverse graph, my inverse function of the cubic function will be reflected over that line. This is not the easiest to draw by hand, but I'm going to try my best. Something like that. It's reflected over the line y equals x. It's symmetric with respect to that. We will talk about that more in class, so don't worry if that just went way over your head. Don't panic. Let's talk about some examples first, and some more basic examples of finding inverse functions. So, we're told these are all one-to-one functions, which is necessary for the function to have an inverse, so that's awesome. We don't have to check for the function being one-to-one, but we can find the inverses. And I just said that we find those inverses by switching x and y and solving for y. So for f of x equals 3x minus 2, f of x, of course, is y equals 3x minus 2. And when I say switch, I literally mean switch their places. So instead of y equals 3x minus 2, I have x equals 3y minus 2. And now I solve for y again. So I add 2 to both sides, and then I divide both sides by 3. So I'm left with x plus 2 over 3 equals y. So that means my f inverse of x is x plus 2 over 3. That's all. That's all I need to do. So let's do b together. I have y equals x to the 5th minus 3 over 2. I switch x and y, so now I have x equals y to the 5th minus 3 over 2. I multiply both sides by 2, so I have 2x equals y to the 5th minus 3. I add 3 to both sides. I have 2x plus 3 equals y to the 5th. And now, to get y by itself, I take the 5th root of both sides. So that means I'll be left with y on the right. And then I have the 5th root of 2x plus 3. So my inverse function, inverse f of x, equals the 5th root of 2x plus 3. Go ahead and try C and D on your own. We'll talk about those in class. We can go over those as examples once we get there. So that's finding the inverse of a function. Not too bad. Let's talk about some properties of inverse functions, or making sure, verifying, that two functions are in fact inverses of one another. So let f be a one-to-one function with domain A and range B. The inverse function, f inverse, satisfies the following two cancellation properties. We have f inverse of f of x equals x, and f of f inverse of x equals x. We're composing functions. We talked about composing functions before. So that means that when I evaluate f inverse for f of x, I should be left with x. And when I do the same thing, I evaluate f of x for f inverse of x, I'll be left with x. Let's go through some examples of that so you can see what I mean. Show that the following functions are inverses of each other. So I want to prove that f of x and g of x are inverses of each other. So that means I need to prove that f of g of x equals x, and I need to prove that g of f of x equals x. So let's start with f of g of x. That's going to be f of g of x is x plus 5 over 2. So that means everywhere I see an x in f of x, I'm plugging in x plus 5 over 2. So I have 2 times x plus 5 over 2 minus 5. Those 2's cancel out. So I have x plus 5 minus 5, which is x. So far, so good. Let's check the other one just to be sure. G of f of x is g of 2x minus 5. So now everywhere I see an x in g of x, I'm plugging in 2x minus 5, and I have 2x minus 5 plus 5 over 2, which is 2x over 2, which is x. So in both cases, both ways, I get an x. That means that I have proven these functions are inverses of each other. And I'm done. So if you see a question like that, that's all you need to do. You are composing the two functions in both orders, and if you get x as your final answer for both of them, then you're good. I'm going to have you do B on your own. And we're going to finish by talking about this last example, example 4. So we're given a graph of f of x, and we're asked to find the domain and range of f first, and then determine the average rate of change between x equals 3 and x equals 8. And then we need to sketch the graph of f inverse. So let's start with A. We have the domain. I go from x equals 2 to 3, 4, 5, 6, 7, 8. So my domain, and those are inclusive, I have closed circles on both sides, is to 8. My range goes from y equals 2 here to 3, 4, 5, 6. Again, that's inclusive. Pretty straightforward. For B, I need to get 2 points and then plug those in to my average rate of change formula. I need x equals 3, so that'll be along here, and that looks like my point here, which is the point 3, 4. And then x equals 8, and that's going to be my point 8, 5. So this is A, f of A, and B, f of B. So when I plug into my average rate of change formula, I have 5 f of B minus 4 f of A all over B, which is 8, minus A, which is 3. So this is 1 over 5, and that is my average rate of change between x equals 3 and x equals 8. Finally, part C. Sketch the graph of f inverse. Careful. We are not even sure that this graph, this function, this f of x, has an inverse. How do we check for that? we need to test. We need to use the horizontal line test. And if I do, I see that right there, I fail my horizontal line test. So this function does not have an inverse. The graph of f inverse does not exist because it fails the horizontal line test. If it did not fail the horizontal line test, then all we would need to do is, remember I said that we reflect it over the line y equals x. So we would just need to plot the line y equals x and then reflect each point on this function over that line. We can go through an example of what that would look like in class together. So for now, don't worry too much about that, but just remember that you always need to test to make sure that there is an inverse. That is about it for inverse functions and for one-to-one functions. Please keep your questions written down, bring them to class, and enjoy the rest of your day whenever you're watching this. Thank you so much.